Now that we can identify the zeros or the roots of my polynomial, we need to be able to determine whether that root or that x-intercept crosses or touches the x-axis. So here I am going to talk about the multiplicity of my zero. That's what this is called. So when we have my zero written in its factored form raised to some power m, if m is even, then we touch the x-axis. If m is odd, then we cross the x-axis. That should be. So even is touch, odd is cross. Let's go back and revisit the polynomial we did in the last video. We have all three roots shown right here. We know that when my function is at -1, something was happening. We know at +3 and at +1/2 we have something going on. Now if you look at the factored form of my root, you can see here that this is x plus 1 raised to the understood first power. We don't see the 1, but it is an understood 1. So if this is a root raised to an odd power, we know that we cross at -1. Here the next root we have at 3 is even, so we're going to touch at 3. And finally the last root, we know that since 3 is odd, we know that at 1/2 we are crossing this function. So let's just see what that looks like now that we could, just using a little algebra and some of the rules for the multiplicity of our zeros, we have kind of a general idea of what this function looks like. So if I were to graph this on the computer, you can see here that I have, and let me see if I can make this just a little bit bigger for you right there. Okay, this is my function. This is my function. I put it into Desmos. I tend to like this calculator, online graphing calculator. And what do you notice? Over here at -1, we are crossing the x-axis. Again, at -1/2, we are crossing the x-axis. And then at 3, we were touching the x-axis. And that's pretty much what we said, right? A cross, and a touch, and using my rules for the multiplicity, we had a cross, and a touch. So let's kind of think about that. We're kind of getting these functions to where we can analyze what the graphs of these functions look like. And if we go back and we determine or we look at the end behavior again of that function that I was showing you in Desmos, let's go back and look at it one more time. What do you see here? You see here that, and I zoomed out so that hopefully you could see the whole thing. Let's go a little larger. There we go. You can see here that my function is going off to infinity in the same direction, right? Both ends of this function are moving to positive infinities, and therefore we know that this would have to be some sort of even-powered function. Let's go back and verify that using the function we have here. So we're we keep revisiting this same guy. If we know ahead of time that this function is supposed to be an even-powered function, right? It should be a degree, the degree of the function should be even. Let's verify that using this idea here. And the way that we approach that is using our rules of exponents. If I were to expand this polynomial or simplify or get rid of all of these parentheses, all that really means is I am going to be multiplying an x to the first power times an x to the second power times an x to the third power. So I am pulling out just what ends up being the leading coefficient of each of these multiplications. And I'm going to use my rules of exponents to be able to say, well, if I multiply and my bases are the same, then all I do is add the exponents up. So if the bases are the same, we add the exponents. So 1 plus 2 is 3, plus 3 more means that if I were to expand this polynomial, the leading coefficient would be x to this, or the leading term, the leading term would be 6, meaning this is a 6th degree polynomial, and that's obviously even, and it does support what we have found. Even though we went ahead and graphed it, we can see that we can get a general idea of what this would have looked like without even having graphed it. So let's see if we can practice that a couple of more times. Here I have two problems for you where I want you to form the polynomial function whose zeros and degrees along with their multiplicities are given. So in other words, I want you to come up with the polynomial function described here. So this is something that I want you to stop the video for, and we'll come back and make sure that we get the same answers. Okay, so hopefully you paused this and you were able to practice. If I know I have zeros at -1, 1, and 3, there's no multiplicity given, so I just set them up in their factored form like this, x plus 1, x minus 1, x minus 3. And when I combine them together, I end up with the polynomial function that looks like x cubed minus 3x squared minus x plus 3. And that represents this problem right here. Notice that this is a polynomial of degree 3, which is what it said it should be. Now the second example was a little bit more involved, because I was given that for each case I had a multiplicity. So in other words, this is the root and the multiplicity of that root. Remember that if I am given a root, then I write it in its factored form followed by the multiplicity. So this first one looks like x plus 1 raised to the first power, and the second root I was given is x minus 3 raised to the second power. So this is my polynomial here, and when I multiply this together, I end up with x cubed minus 5x squared plus 3x plus 9.